So our topic for tonight is linear equation of order 1. So if you see the title of the video, so this is all about the integrating factor. So integrating factor. So what is a linear equation of order 1? So by the definition itself, the linear equation of order 1 is a differential equation wherein the order of the derivative is in the first order. So y prime in some nomenclature, and also it is a linear. So when we say linear, the involved variables are two-dimensional, which are x and y. Okay, so from the beginning of the first topic about solving the solution of a differential equation from the separation of variable up to this topic, so we are dealing with linear equation. Now in this one, we are clearly emphasizing that the order of our differential equation is in order 1. So it is linear in order 1. So the standard form of a linear equation of order 1 is given with the formula e of x, dy dx plus b of xy is equal to c of x. Okay, so that is our standard form of a linear equation of order 1. So wherein our a is a coefficient, it is a function of x. So it could be, for example, it could be x plus 1. We could have dy dx plus, maybe I will write this one in a different color of pen. Okay, so x plus 1, so this is dy dx plus, so our b of x, so again this is a function in terms of x, so we could have that one as x squared, so y, then our c of x is equal to, c is a function, c of x is any function which is a function of x, so we could have that one as maybe x. Okay, so this is an example of linear equation of order 1. So in order to solve this type of differential equation, we must find a way so that this differential equation could become an exact equation. So exact equation. So because this type of equation could not be solved directly because of this function here, the c of x. So that's why we are going to find a way in order for this equation to become a exact equation. Okay, so the first method is by getting the integrating factor. Okay, so you could have this one as the integrating factor method. Okay, so if you are going to do this method, so we will just copy first our standard form. Okay, so we have now the standard form. So suppose if you are going to divide both sides by this coefficient, so the a of x, okay, a of x, then we could have dy dx plus b of x over a of x, y is equal to c of x over a of x. Okay, so we will just simplify this further. So we would say let b of x over a of x equal to p, then our c of x over a of x is equal to q. So substituting this assumption, so our equation now will become dy dx plus p y equal to q. Okay. Now this p, our p here, so the p is, that is, as we know from the above equation, that is a of x over b of x over a of x. So our p here is the k for us in order to get the integrating factor. Okay, so how we are going to do that? So the integrating factor, as per definition, okay, so the integrating factor is equal to the exponential function raised to the power of the integral of our p dx. Okay. Now, this integrating factor is applicable if our x is the independent variable. So we are considering the dy dx. So of course, if we have this one in reverse, so we could have our integrating factor, so maybe in terms of y, so if, so the integrating factor is p of integral of p dy, wherein our p here is b of y over a of y. Okay, so these functions now are in terms of y because our y is the independent variable, but the method of solving this one is just the same. So we are just interchanging the variables. So we are making our y as the independent variable and our x as the dependent variable. Okay, so how do we solve linear equations of order 1 using this method? So we have the steps. Okay, so first, so we must put the equation in the form, so the form which is the form that we have derived a few moments ago, so that is p y q. Okay, so this one, this equation. Okay, so this form. Then second, step 2. Step 2 is obtain the integrating factor. Integrating factor, so which is equal to if is equal to e integral of p dx. Then the last one, to get the general solution, so solve the resultant as an exact equation. Okay, so we have 3 steps in solving linear equation of order 1 using the integrating factor method. So first, we need to put the equation in the form dy dx plus p of y is equal to q. Then the second is obtain the integrating factor. So our integrating factor is equal to e raised to the power of the integral of p dx. Then solve the resultant as an exact equation. Okay, so the steps are somewhat very easy to follow, but the question is how to apply that one in the actual or in a given differential equation of order 1. So the first method in which we are going to test the equation is linear exact equation or homogeneous equation. So this type of solution or this type of differential equation can be determine by just looking, or by inspection, just looking at the given differential equation. So if the given differential equation is like this one, okay, like this one, then you could say that that differential equation is an equation, a linear equation of order 1. Of course, by doing that, we could use the integrating factor method. Okay, so let's apply that one by an example. Okay. Okay, so let's have our first example. So we have 2y minus 4x squared dx plus x dy is equal to 0. Okay, so this one is, per inspection, this is now a linear equation of order 1 because of this term, the xy dy. And if you are going to inspect or use the method of exact equation or homogeneous equation, so this is somewhat cumbersome to attain or to solve. So for this one, we just use the linear equation of order 1. So in solution, so the first step is to put the equation in the form, this form, dy dx plus p of y is equal to q. So how we are going to do that? So we'll just divide both sides by dx. Okay, just copy first the original equation, 4x squared dx, okay, plus x dy is equals to 0. Then divide both sides by dx so that we could have dy dx. Okay, so we will have 2y minus 4x squared. So the dx are already cancelled. So we have x dy dx is equal to 0. So we'll just rearrange this one. So we will have x dy dx, then plus, maybe we should transpose, or we should distribute our 2 here to this quantity. So we'll have 2y minus 8x squared is equals to 0. Okay, so this is a pure function of x. So we could say that from the given standard form of our linear equation, so this is a pure in terms of x equation. So for our example, this one here, the 8x squared is c of x. So we could transpose this one to the other side of the equation. So we have x dy dx plus 2y is equal to 8x squared. Okay, now we will convert this one into the standard form. So in this form, we could say that our a of x is, maybe we should have another color for this one. Okay, so this is now the form of our linear equation of order 1. So by inspection, we could say that our a of x is equal to x. Our b of x, so the b of x, going back to our standard form, that is the function of x which is accompanied by y. Okay, so if we are going to look this one, so the b of x, so the term or the function that is accompanied by y is our 2. So we could say that our b of x is 2, and our c of x, so as we have shown a while ago, that is 8x squared. Now, in order for this one to become a linear, the form in which we could apply the integrating factor, so we must divide both sides by a of x. So our a of x is equals to x. So what will happen now? We will have dy dx plus 2xy, or you could have that one 2y over x, but this one is just the same. Then this is 8x squared over x. Okay. Then, simplifying further, you have dy dx plus 2xy is equal to 8x. So now we have arrived in the form in which we could get our integrating factor. So our p of x here is our 2 of x. So p is equal to 2 over x. Okay. So getting the integrating factor is equal to e raised to the power of p dx. So we have e raised to 2 over x dx. So the integral of 2 over x dx. So going back to your integral calculus, so the integral of a exponential function, okay? So this is equal to e. So we could transpose or transfer our 2 to the outside the integral sign because this is constant. So we will have 1 over x dx. So clearly this is ln x. So we will have integral of 2 ln x. Then using the properties of logarithms, we have e ln x squared. Okay. Then this could be cancelled out so that we could have only our abscissa here, so that is equal to x squared. So this is now our integrating factor. Okay, so our integrating factor will be multiplied to the both sides of the equation. So this one. Okay, so we will have this one as this form of the equation. Okay, so dy dx plus 2 of x y is equal to 8x. Then we will multiply that one, x squared. Okay, so we will end up with x squared dy dx plus, that will be 2xy, okay, is equal to 8x cubed. Okay, so if you are going to solve for this one, okay, this part here, neglecting this part, so this part is an exact equation. So the shortcut for that one, so that we will not be going to the exact equation part of solving this one. So we'll just copy the integrating factor, which is x squared, then multiply that one with the dependent variable of our given dE. And for this one, this is y. So we have x squared y. Then this one will be integrated, the q here, x cubed, integrated in terms of x. So we have now 8x cubed dx. So that is x squared y is equal to, okay, so we could transpose our 8 to the outside part of our integral. So this is x cubed dx. Then we have 8, 3 plus 1, x 3 plus 1, so that is plus c. So our final answer is equal to x squared y is equal to 8 over 4 x to the 4th plus c. Okay, simplifying this one further, we will have x squared y is equal to 2x to the 4th plus c. Okay, so this is now our answer. Okay, so of course you could do the exact equation in this part alone, because the exact equation part of this, after multiplying both sides of the equation with the integrating factor, is this one. Okay, so this will be your n and this will be your m. Then you could do the method of exact differential equation, and you will end up with this one here, the x squared y. Then this one, just do the integrating in the integral part of the solution. So that is the answer for our first example. So if there are any questions, so you could type on our chat box. Okay, you could type in our chat box, the live chat, or in our group chat. Okay, so that there will be no confusion. So in your Google Classroom, I have already posted the set work for this one, so you could also glance on that one in advance, and also the link for the video of this one. If this will be after the live stream, this will be also uploaded. Sorry for that. It will be uploaded on YouTube, so that you could also review the whole session, the whole discussion. Okay. So maybe we will go to a much difficult, okay, example, because sometimes the students would say that the teacher will just be giving an example that is easy, and when the quiz comes, the problem on the quizzes are difficult. So I will also solve a somewhat difficult problem. Okay, so as you can see, I have adjusted also your quizzes. So on your first few quizzes, so you are given 1.5 hours to pass, and the time allotment for your quizzes will also change, or will also increase depending on the difficulty of the topic. Okay, so as of now, I am currently checking your papers, your submissions, so on the submission link, and also your prelim exam. Okay, then maybe a week or 2 weeks from now, you will get your prelim grade. Okay, so I just hope that some of you who have messaged me saying that you are unable to pay your duties or your payments for the prelim. So I hope you have already paid that one, so that there will be no so that you will not be graded in G on for the prelim term. Okay, so let's proceed. So we have here our example number 2. So y prime is equal to x minus 2y cotangent 2x. Okay, so the dread of all engineering student, any topic or any branch of mathematics which included a trigonometric function or a trigonometric identity is a dread to any engineering student. So when it comes to differential calculus, when there is now the topic of getting the derivative of trigonometric functions, in which the given is involves trigonometric identities, so the student will be somewhat scared to see those functions. When it comes to integral calculus, the same. Now on DE, I guess it will be the same, but nonetheless, the trigonometric part, or the trigonometric function of any branch of mathematics is easy as long as you are familiar with the trigonometric identities. Okay, so the first one is the equivalent for the trigonometric functions, the 6 trigonometric functions. So we have the sine, cosine, tangent, secant, cosecant, and cotangent. So you must know which of those functions is a reciprocal of the others. So that is the first. Then we have the Pythagorean identity. So the sine squared x plus cosine squared x is equal to 1. Then we have the secant squared is equal to 1 plus tangent squared x. So that is the Pythagorean identity. Then after that one is the sum and difference of two angles. Then the next one is the double angle identities. Then the half angle identity. So I believe that is the trigonometric identity that you can use in this topic or all other topics in mathematics. Okay, so going back to this question, so we have y prime is equal to x minus 2y cotangent x. So by just looking at this one, we know now what is the identities that we are going to use. So for cotangent x, so we know that cotangent x is the reciprocal of tangent, and tangent is equal to sine x over cosine x. So you have now the idea on how to attack this problem. So we'll just use the term attack. Okay, so first we'll just the step one is to get this one in the standard form. Okay, so we have dy dx x minus 2y cotangent x. Okay, so we'll divide both sides by dx. So we have dy is equal to x minus 2y cotangent 2x dx. Okay, then okay, so maybe we'll not be dividing this one by dx. Okay, so because this is already in the standard form. Okay, so we go back here with dx. Okay, so we will try to determine in this equation here, which is our a of x, b of x, and c of x. Okay, so our dependent variable is x, and our independent variable is x, and our dependent variable is y. So we have this one. So this is our b of x, and this is our c of x. So we'll just arrange this one. So we have dy dx plus, we just transpose this one to the other side of the equation. 2y cotangent 2x is equal to x. Okay, then we will just we'll just determine now which is our a of x, b of x, and c of x. So for this one, our a of x is equal to 1. Then our b of x is equal to 2 cotangent 2x, and our c of x is equal to x. Okay, then we'll just be dividing both sides by our e of x, which is 1. So we still end up with the same equation. So dy dx plus 2y cotangent 2x is equal to x. Then we need now to get our integrating factor. Okay, so our integrating factor, so that is our p. So this one, this is our p. Okay, so our p is equal to 2 cotangent 2x. Okay, so now the integrating factor is e raised to the integral of p dx. So we have just move it down here. Okay. So we have E integral of 2 cotangent 2x dx. Okay. Okay, so now we just need to get the integral of 2 cotangent 2x. Okay, so let's consider integral of 2 cotangent 2x dx. So we have 2 cotangent 2x dx. So the identity for this one is 2 cosine x over sine x dx. Okay, so this is not sine x but sine 2x and cosine 2x. Okay, so our function here, our u, if you go back to our integral calculus, so u is sine 2x, the du is 2 dx, so du is 2 cosine 2x dx because our u is sine 2x. So our integral is in the form of du over u. Okay, we have the du, which is 2 cosine 2x dx. We have also the u, which is sine 2x. So we could say that the integral of this one is ln sine 2x. Okay, then substituting this one to the integrating factor, so we have e ln sine 2x. So from our concept of exponential functions, we could drop the eln, so we just have sine 2x. So this is now our integrating factor, in which we are going to substitute this one to this equation. So we will have sine 2x dy dx plus 2y cotangent 2x sine 2x is equal to x sine 2x. Okay, so this part of the differential equation is just an exact equation, in which the answer of this one will be just y sine 2x. In the other part, in which we are going to integrate, so x sine x 2x dx. So we have two transcendental functions which we are going to integrate. So this can be solved only using integration by parts. So going back to your integral calculus again, so consider integral of x sine 2x dx. So we know that the integral of u dv is equal to uv minus v du. Okay, so we need to choose which is our u and our v. So let's just say that our u is x. So because x could be derived into dx, and the function will terminate, then our dv is sine 2x dx. Okay, so the integral of that is negative 1/2. So the 1/2 is for the cosine 2x, or for the 2x. Okay, then we just substitute this one to the form of the integration by parts. So we have integral of x sine 2x is equal to uv. So we have negative 1/2 x cosine 2x, then minus integral of negative 1/2 cosine 2x. So this is our v, so that is v du, so this is dx. Okay, so we'll end up with negative 1/2 x cosine 2x, so this will be plus, so the integral of 1/2 cosine 2x dx is this is sine, then we need the derivative of our 2x, so that is 2, so we'll have 1/4 sine 2x plus c. Okay, so this is now the integral of x sine 2x, so the right side of our equation. So we'll end up with the general solution now is y. Okay, maybe we'll have this one in orange. Okay, so we have y sine 2x is equal to negative 1/2 x cosine 2x plus 1/4 or 1/4 sine 2x plus c. Okay, so multiplying both sides by 4. Okay, so we'll end up with 4y sine 2x minus 2x cosine 2x plus sine 2x plus c. So we just arrange this one. So 4y sine 2x is equal to c plus sine 2x minus 2x cosine 2x. So this is now our answer. Okay, so I think that will be all for this evening. So our topic of linear equation of order 1. So we will solving it using the integration factor method. So now you will be doing your sheet work. Okay, sheet work 3. So you just go to our Google Classroom. I believe it is already posted. Okay, so you just click on the Google form. If you want to review this video, so you could also click the link, so it is also included on the sheet work, the link for this video. Okay, so if you have any question, you could type on the chat box so that we could answer it. So any clarification on the solution of the examples. Okay, so I believe there is no questions. So thank you for your time. Thank you for attending our online discussion. So you could now go to our Google Classroom and answer the sheet work. And next meeting we will have our quiz. Okay, so thank you and good night.
One, two, three.